Hello and welcome back to set theory. Today we're going over set difference. So the difference of the sets A and B is the set of things which are in A but which aren't in B. One way to intuitively understand this is if you have these two circles here representing the sets A and B, the difference of A and B is going to be this region right here. So it's the set of things which are in A but which aren't in B. So you cut away any overlap. As long as A and B exist as sets, then we know this set has to exist too by the axiom schema of separation. In this case, this part right here would be our P of X. If you don't know what that is, go watch that lecture first. Let's do a quick example here. Assume A, B, C, D, and F are distinct. We want to find what's the set difference of these two sets going to be. Okay, well, here's the thing. It's just the set of things that are in this set, but not in this set. Okay, so we see A is in the first set, but it's not in the second set. So our answer is going to include A. B's in the first set and not in the second set, so it's going to include B. What about C? Is C going to be in this set? Well, the thing is, it's the set of things that are in the first set, but not the second set. So since C is in the second set, then C cannot be in this set. And similarly, D can't be in our answer either because D is in the second set. Likewise, E and F can't be in our set because, well, for one thing, they're in the second set, so they can't be in here. But also, they don't appear in the first set at all. So even if they weren't here, they wouldn't be able to appear in the answer anyway. All right, so that means the set of things which are in this set, but not this set, is the set containing just two elements, A and B. Now, just a note, some books write A minus B or A squiggle B for the exact same concept. However, I'm using A backslash B because I think that's the most mainstream. Here's another example. If you have a set A, then the difference of A with the empty set is just going to be A. The reason for that is that this is just the set of things in A which are not in the empty set. But since the empty set contains no elements, this part's always true. So the set of things which are in A for which true is just A. What about the set difference of A with itself? Well, it turns out we just get the empty set. And the reason for that is if you start with the set A, but you take away all elements of A, well, then you have nothing left. More formally, this guy's just the set of things in A which are not in A. And since you can't both be in A and not in A at the same time, there's nothing that can possibly be an element of this set. So this set has no elements, so it's the empty set. All right, now what about this? Well, if we start out with the empty set and we take away anything that's in A, well, then we just get the empty set. And the reason for that is if you're in this set, that means you're in the empty set, but you're not in A. But here's the thing, if you're in the empty set, well, that's impossible. So there's nothing that could possibly be in this set. So this set has to be empty. All right, now let's try to prove a few useful identities involving set difference. How do we prove this one? Well, if you're in this set, that's the same as saying you're in A and you're in this set. But what's this the same as? Well, saying you're in B minus C is the same as saying you're in B, but you're not in C. So we can rewrite this part as just saying X is in B and X is not in C. Now, since and is logically associative, we can move the parentheses. But what's this first part right here saying? Saying X is in A and X is in B? Well, that's the same as just saying X is in the intersection. But now saying X is in the intersection and X is not in C is the same as saying X is in the difference of the intersection with C. So these two sets right here have to have the same elements, and so therefore they must be equal. Here's another easy theorem. Being in this guy is just the same as saying you're in A, but you're not in B. Being in this guy is the same as saying that you're in A, but you're not in the intersection. In other words, you're in A, but you're not in both A and B. Well, being in A, but not in both is the same as saying you're in A, but not in B. Since they're logically equivalent, the sets must be equal. Here's a similar theorem, but involving unions instead of intersections. Well, here's the thing. Being in this set means that you're in at least one of A or B, but you're not in B. Well, here's the thing. Being in at least one of them, but not in B, is the same as being in A, but not B, which is the same as saying that you're in this set. So that proves this. Here's another easy theorem, and this one's kind of cool because it lets us rewrite intersections in terms of just set difference alone. So how do we prove it? Well, let's start by analyzing the more complicated looking side first. Let's say X is in this set. Well, what's that the same as saying? Saying X is in this set is the same as saying X is in A and X is not in this set. Let me rewrite X as not an element of this set like this. Well, this part can be rewritten like this. Well, here's the thing. Saying that it's not true that X is in A and X is not in B is logically equivalent to saying that X is not in A or X is in B. The reason is that saying some and statement is not true is that's the same as saying that at least one of these guys has to be false. So you can distribute the not and it changes into an or statement. All right, now saying that this and statement is true is the same as saying this has to be true and this has to be true, or this has to be true and this has to be true. All right, but here's the thing. This part right here, this is always false. So the or statement just simplifies to this part. So this logical statement can be simplified to just this. And what is this the same as? This is the same as saying X is a member of the intersection. And that concludes the proof. Since these two guys have the same exact elements, that means these two sets have to be equal. The next two theorems are called De Morgan's laws for sets. These are named after the famous De Morgan's laws for logic. Saying that it's not the case that P and Q are both true is the same that saying either P has to be false or Q has to be false. Likewise, saying that it's not the case that at least one of P or Q has to be true is logically the same as saying P has to be false and Q has to be false. So these logical laws let us distribute the not to an and change it to an or vice versa. Now, the set theory version is a little more complicated because if you have a set A, well, the set of all things that don't belong to A, well, that doesn't exist because if it did, you could take the union of these and get the set of all sets, which we know doesn't exist by Russell's paradox. However, this theorem here is kind of the closest thing to this. Top one says that if you're in C, but you're not in both A and B, that's the same as saying either you're in C but not in A, or you're in C but not in B. The bottom one is saying that if you're in C but you're not in at least one of A or B, well, that's the same as saying you're in C but not in A, and you're in C but not in B. So let's prove them. B in this set, what's that the same as? That means you're in C, but you're not in this set. In other words, you're not in both A and B. In other words, this is the same as saying you're in C, and it's not the case that you're in both A and B. Okay, but now by De Morgan's law from logic, we can distribute this not sign and change the and to an or. Okay, so this is the same as saying X is in C and either X is not in A or X is not in B. And just for convenience, I'll rewrite it in this notation just to have less symbols. All right, but now what's this the same as? Well, there's also a logical law that says and distributes over or. So this is logically equivalent to saying X is in C and this is true, or X is in C and this is true. But now this part right here, being in C but not in A, that's the same as saying you're in the set difference of C and A. And likewise, this part's the same as saying you're in the set difference of C and B. So now if you're in here or you're in here, that's the same as saying you're in the union. So that's the same as saying that X is in this union right here. So that means these sets have to be equal. All right, now let's prove the second part of De Morgan's law. Being in this set is the same as saying you're in C, but you're not in this union. So this is the same as saying X is in C, and it's not true that X is in the union. Okay, now this part we can rewrite like this, X is in A or X is in B. But now we can use De Morgan's law from logic to distribute this not sign, but then our or symbol changes into an and. So we can rewrite it like this. And we can rewrite that in more compact notation. Okay, now saying this means you're saying that all three of these things have to be true, right? That's logically the same as saying that all four of these things have to be true, right? Because this one I just doubled. We're taking advantage of the commutative and associative laws for and here. But in particularly, I can basically put the parentheses anywhere I want. I can put parentheses right here and it'll still be logically equivalent, right? And why am I doing that? Well, that's because the first part here is just the same as saying X is in the set difference of C and A. And then the second part is the same as saying X is in the set difference of C and B. So when I say X is in this set and X is in this set, that's the same as saying X is in the intersection of those two sets. So that's the same as saying that X is in this set. So we've proven this set is equal to this set. And so that proves both of De Morgan's laws. And here's another useful theorem. If you have one set that's a subset of the other, then if you have the smaller set difference with taking away the bigger set, then you're just left with the empty set, and vice versa. So let's prove this. And since it's an if and only if, we'll prove the forward direction first. Assume A is a subset of B. Well, guess what? If A is a subset of B, then our set difference, in other words, this set, has to be empty. And why is that? Well, since everything in A also has to be in B, then it's impossible for something to be in A, but to not be in B. So this set has no elements. So therefore, this set equals the empty set. The converse direction, assume this is true. Assume that the set difference is empty. That means this set is empty. So that means there's nothing in A which is not in B. Since this set has no elements, that means it's impossible to be in A without being in B. In other words, anything that's in A has to also be in B. And of course, that's just the same as saying A is a subset of B. Here are all the properties we covered today. You don't need to memorize these, but you may want to add them to your notes. The important thing is to know how to derive these when you need them. Like and subscribe if this was helpful, and I'll see you in the next lecture.